Hello all, I want to welcome you back to our lecture series, and today we'll be looking at gas laws problems. Remember, in the first section or in the first part of this lecture, we started talking about the gas laws, and I introduced all the gas laws that we'll be considering, and we looked at their theoretical background and the relationships involving the various gas parameters. In this particular lecture, what we're going to be basically doing is to just solve problems in all those gas laws in consideration. But first, as usual, we're going to talk about our quotes. Now, the quote is from Ralph Waldo Emerson. It says, "When it is dark enough, you can see the stars." At that point, when you think there's too much adversity, there is too much difficulty, I just want to give you something. That is, at that point in time, there is always a ray of hope and a ray of deliverance. And that is exactly the meaning of this quote. And let's take it off from there immediately. Again, here we'll be considering the same learning objectives like we talked about in the first part of this class. We talked about the kinetic theory of gases. We talked about how to convert pressure and temperature to one another. However, in this particular lecture, in this particular video, I'll be addressing how to do calculations based on the gas law and this particular general gas equation, the ideal gas equation, and Dalton's law of partial pressure. These are those ones we're going to be considering in this class. Let's take it off from there. Problem 1. Like I said, we're just solving problems. We've already known the theoretical backgrounds of these laws. Now we're going to be applying them in solving problems. The question says, a 350 ml sample of an argon gas at 7 degrees Celsius, 7.0 degrees Celsius, and 790 torr is transferred into a bigger cylinder with 620 ml. So what pressure would the gas exert in a cylinder at 47 degrees Celsius? If you look at this problem now, one thing that first comes to mind is that which law is being addressed here? Now, usually I tell students the best way to know which law is being addressed is to look at the parameters you're given. The parameters that we're given here is, if you look at it, you're given every other variable in 2s. And one of them is not given in 1. Let's count it. We have a temperature in 2, so this will likely be T1 and T2. We have a volume in 2. This is V1 and V2. And we only have one pressure, so we need to have two pressures as well. And that is what the question says, what pressure? So this question is addressing the general gas law. That is what we want to do here. And what formula we're going to be using? Remember, the general gas law formula, you'll always be given that in exam, is P1 V1 over T1 equal to P2 V2 over T2. And remember again, it is your responsibility to do what? Write out what you have, isolate the information you have correctly, so that that's going to help you to solve the problem. So let's start from the initial condition. What do we have? At the initial condition, we can start with any one. So what it means, this is our V1. So the V1 is, the ones represent the subscripts one represent the initial condition. We have 350 mils. 350 mils. And then what else do we have there? So what it means is that in our T1 is going to be the temperature. So the temperature in Kelvin, of course, remember, the temperature has to be in Kelvin temperature. Every temperature has to be converted into a Kelvin temperature. So our T1 here is going to be, of course, is going to be 7 degrees Celsius plus 273. And when you add that up, you're going to be getting 280 Kelvin. That is our. And then our initial pressure will now be, remember the pressure started with 790 torr. In doing general gas law, you do not need to do what? You don't have to do what? Convert the pressure unit to atmosphere or the volume into liters, because it's going to cancel out. So this is our initial condition. I'm going to try to isolate it. This is what we have at the initial condition. That's what we have. He said this now is being transferred into a bigger cylinder of this volume. Now, Let me select the second condition. The second condition, V2, there is going to give me 620 mils. That's what I have there as mine. Then my T2, of course, is going to give me 47. So that again, what is going to do is you're going to say 47 degrees Celsius plus 273. And that's again will give us, when you add 47 plus 273, it's going to give you 320 Kelvin. And then what is our P2? Of course, we don't have it. Our P2 is what we're looking for. And since the initial pressure was in torr, the second pressure has to be in torr. And we're going to see this at the moment we cancel. Having done this to this side, we're going to use the right to solve this problem. Let us isolate. Now, there are two ways you can do for this. Since we want to solve for, I'm going to use blue this time. Since we want to solve for the initial pressure, which is P2, you can first of all make P2 subject of the formula from here. Or, what do? Or you put the numbers and then rearrange the equation. So, whichever one that suits you, you can do it. So, what I'm going to do now is that I'm going to put the numbers. In putting the numbers, P1, my P1 here is 790. So, I'm going to say 7, let me make it a little bit up. So, it's going to be 790 torr. Remember, you put your unit times P1 times V1. Our V1 is what? 350. We isolated that already. 350 mils. That's what we have here. Divided by T1. What is our T1? Our T1 is 7 degrees Celsius, but we converted it to Kelvin. So that gives us what? 280 Kelvin. And this will be equal to P2. P2 will give you what? Again, what are we going to do? Our P2 is what we're looking for, remember, which is this pressure. So we're going to have it as P2. We don't know it. And P2 will be multiplied by V2. What is our V2? We come here. V2 is what? 620 mils. And then divided by our T2 is going to give us 320 Kelvin. At this point in time, we're halfway done with this work. What else do we do? We're going to rearrange this equation. So in rearranging this equation, I usually tell students, the first thing I want to do here is to cross multiply. Now, for some of you that did math prep for this class, these are kind of things you should have done, but I'm still going to do it at least in this first problem. So I'm going to cross multiply those two. So if you cross multiply this, what does that give you? So it's going to be all you have here times this. So we're going to have all this guy times itself. So we're going to have, we're going to have 280 Kelvin times P2 is on its own times 620 mils. Will be equal to, we're making this by cross multiply, we're making it a linear equation times everything you have here. So this is going to give us 790 torr. 790 torr times 350 mils times 320 Kelvin. What else do we do? We need to isolate P and allow B alone. So how do we do that? We divide all sides by these two that we want to eliminate. We need to eliminate these two and leave P to be alone. So what will I do? I'm going to divide both sides by 620 and this. So I'm going to divide this side by 280 Kelvin times 620 mils. And again, I'm going to divide this side 280 Kelvin times 620 mils. So if I cancel, let's cancel. If you cancel, let's see what that gives us. Now, the whole of this guy, we cancel the whole of this. The whole of this, we cancel the whole of this. And again, what are you going to be left with? You're going to be left with P2 will now be everything here. 790 torr times 350 mil times 320 Kelvin divided by 280 Kelvin times 620 mils. And when you put this in your calculator, you're going to be getting approximately 510 torr. and that becomes your answer. So now in the next problems, I'm not going to be going step by step in showing you how to cross multiply and how to cancel, but I'm doing it in the first problem just to remind you some of this process in case you've forgotten how this is done. This is how we do the first problem. Let's move on immediately with the second problem. Still on there. The second problem says an 8.0 liter sample of ammonia gas was collected at this temperature 63.0 and a pressure of 0.75 atm. It says what volume would the gas occupy at 10 degrees Celsius and this. So now you look at that, we're looking for the V2. This is still general gas law. So this is still the general gas equation. So what are we going to do? Again, I want to get my red back. That's what I like using red. And so I'm going to try to isolate all the conditions I have here. So let me try to isolate them first. My initial pressure is 0.75 atm. And then, so you can always write your conditions whichever way you want. Then my initial volume, V1, is 8.0 liters. My initial temperature will be, what temperature? 63. So if you add 63.0 degrees Celsius plus 273, that actually is going to give us 336 Kelvin. This is the initial conditions. So this is our initial conditions. We've gotten everything there situated. Let us get our final condition. Our final condition says what volume. So we're looking for the volume, but we still have our what? Temperature and pressure. So I'm going to start again. My final pressure is going to be 1.4 atm. My volume is what I'm looking for. I don't know. So it's going to be question mark. However, because the unit of this one is in liters, it's going to also be in liters. And finally, our temperature is going to be 10 degrees Celsius. So second temperature is going to be T2, will be 10 degrees Celsius plus 273. That will give us 283 Kelvin. This becomes the final condition. Remember, this is initial. This is the final conditions. Then what do we do? Again, we're going to use the formula. Remember the formula once again. Formula is P1 V1 over T1. I ask students, if you want to solve this problem, just write your formula. Despite the fact that you know it, just always write it. So if you plug everything in from here, what are we going to get? We're going to get P1 is 0.75 atm. We multiply 8 liters, 8.0 liters. We'll divide the initial temperature of 336 Kelvin. And this will be equal to 1.4 atm times, we're looking for the V2, we'll divide that by what? 283 Kelvin, which is the final temperature. And then when we rearrange for V2 again, you're going to do the same process. You cross multiply this, and if you cross multiply, now another way I usually tell the students, another shortcut to use is that the side of cross multiplication that has the unknown will be your divisor. So what it means is that this side now has the unknown. What it means, I'm going to multiply this and divide it with what I have here when I cross multiply. So here, if I do that shortcut, it's going to just go be V2 will be, I'll multiply this one that has everything in it, atm, 8.0 liters times 283 Kelvin. I divide this by these two, 336 Kelvin times 1.4 atm. And if you cancel, let's see if everything cancels. This we cancel this, atm we cancel atm, and the answer will remain in liters like we said. So here your V2 finally, when you do your calculation, well, it's going to give you 3.6 liters. So actually that is exactly what you have here. So your V2 is going to be 3.6 liters. I'm not sure if I did it in the other one. I'm not sure. Oh, I didn't even cancel in this one, but it's fine. If you're going to cancel here, let's see. This will give this, we cancel this. Kelvin, we cancel Kelvin. And your pressure is going to be in tau. All right. It's always important you try to cancel your work because that eliminates a lot of confusion. Let's go to problem 3. In problem 3 again, it is also another. Now, you remember my strategy in a class, in my class is usually to solve as many problems as possible because that helps the students to navigate the problems themselves and understand them. So feel free to pause this video at this point in time, solve this problem yourself, and get back to it to check if you are correct. All right. Okay, let us take it off from there. Now, it says a 9.7 liter gas is collected at this temperature and pressure. The temperature and pressure is given here, respectively. Oh, this is, yeah, okay. This should be small letter, please. It's the continuation of that sentence. And then it says the gas is transferred to this volume at the pressure of this. So what must be Celsius temperature be? So we're looking for the Celsius temperature. Now, you have to be wary of that question because when you solve the problem, your answer is initially going to be in Kelvin. So you now need to get the distance. So let's isolate our conditions. The initial conditions, or P1, is going to be, initial pressure is going to be 1.2 atm. And then you can always do that this another way. You look for your P2. Your P2 given will be 0.950 atm. So I've gotten my P2. So at times you can do this way. Try to get your immediately all the variables of the same unit before you go to the next. So I'm going to go to my volume. So my volume will be V1. Initial, if you look at it, the initial one is going to be 9.70 liter. And then, so what is my V2? It was transferred to a new one. So this is my V2. It's going to be 2.50 liter. And then it says, what must the temperature be? That means I'm looking for my V2, but initially I have my what? My T2, but I have my T1 to be. So my T1 is 37 degrees Celsius plus 273. If you add that together, it's going to give you 310 Kelvin. However, the T2 is what I am looking for at this point. I don't have it. That's what I'm looking for. And so if you calculate initially, it's going to be in Kelvin. However, I need to convert it again to Celsius because that is my main problem in the question. So let's plug everything in. If you plug everything in, so remember the formula is P1 V1. So my P1 is going to be, again, I'm going to write it P1 V1 over T1, P2 V2 over T2. So my P1 is going to give me 120 atm multiplied by V1 is going to give me 9.70 liters divided by T1 will give me 310 Kelvin equal to, what's my P2? 0.950 atm times, where's my V2? V2 is 2.5 liters divided by, I'm looking for my what? T2. And again, if I solve the problem, remember, if I cross multiply, what I'm looking for will be on this side. What it means, these sides are going to multiply and this 2 is going to divide it. So my T2 will basically give me, multiply all these guys without the unknown. So it's going to be 310 Kelvin times 0.950 atm times 2.50 liters divided by these two, 1.20 atm times 9.70 liters. And then if I cancel this, let's see, you find that a liter is going to go with liters, atm is going to go with atm, and the answer I get finally is going to give me, in any answer I'm going to get here will give me 63.3 Kelvin. But the question says, what is the what? The temperature in Celsius of the gas. So I'm going to convert it. To convert this to Celsius, remember again, how do you do that? To convert from Kelvin to Celsius, you subtract 273. So degrees Celsius simply means 63.3 minus 273. And when you do that subtraction, it's going to give you negative 209.7 degrees Celsius. And this is a negative, please. Let me write it well. and that will give you, so this is going to be negative, and this is going to be our final answer. So if you round that off, we're approximately going to get negative 210 degrees Celsius, and this becomes our answer. Always feel free to pause this video, try these problems, and come back to it. All right, now let's go to our next problem. You can pause the video, try out this problem and now let's get back to it. Now this one is easy because I tried to make it a little bit direct. It said use the ideal gas law. I even stated it. Use the ideal gas law to calculate the volume of 0.650 moles of oxygen gas at a temperature of 25 degrees Celsius and a pressure of 1450 millimeter mercury. It says, now it gives you the gas constant. Now, the ideal gas law is the one that you are usually given the gas constant R. And the ideal gas law, of course, always try to write the formula for as I tell student. In ideal gas law, this is ideal gas. In ideal gas, the formula given is usually PV is equal to nRT. Let's isolate what we have all here before we solve the problem. Now we have the number of moles to be given, so we can write that. So number of moles simply means N. So N is 0.650 mole. What else we're given? A temperature 25 degrees Celsius. So our T 25 degrees Celsius plus 273. That's actually going to give you 298 Kelvin. What else do we have there? Then we're given the pressure. Now, remember, for this formula to work, I said it when I introduced the gas law. You have to convert every of your pressure, if they're not in ATM, to ATM. Every of your temperature has to be in Kelvin. Every of your volume has to be in liters. So let's see what we're looking for here. The pressure is this, so we have the P to be 1450, but we can't use it. It's 1450 millimeter mercury, but we have to do what? Convert it to what? To ATM. And doing that, what do we do? Remember, of course, 1 ATM, remember this, 1 ATM is equivalent to, you're going to be given this 760 millimeter mercury. So what that simply means is that we want it to be in ATM. ATM is going to be on top. Our 760 mercury is going to be on the bottom. And then if I cancel this stuff, millimeter mercury cancel millimeter mercury, and then this actually is going to give me, when you do the math, it's going to give you 1.908 ATM. And then, do we have what we're given? Now, we have the gas constant already given to us here, so I don't know to write it. And then we're looking for the volume. We don't have the volume, so I can just say volume. So V, I'll just say question mark. Of course, because of this formula, it's going to be in liters. So if we apply everything we have here, let's plug it in. If we plug in everything we have here, what are we going to get? We're going to have long equation. So it's going to be, from volume, it's going to be 1.908 ATM times volume. Volume is what we're looking for, so we're going to say V. This will give us equal to N. Our N is 0.650 mole times the R is a constant, so it will give us 0.0821 liters atmosphere per mole per Kelvin. Then times my temperature is 298 Kelvin. Now, I would like students, you can start canceling from here. Nothing is bad about it. If you cancel from here so far, what do you get? Let's see. If you cancel from here so far, what do you see? Kelvin, we cancel Kelvin. Moles, we cancel moles. So what you have here for now is liters and atmosphere. So let's continue. So solving for V, I'm going to divide both sides by this. So I'm going to divide this side by 1.908 ATM. Divide this side by 1.908 ATM. So if it cancels again, let's see. If this guy cancels this guy, we're going to have everything left on that side. So basically what we have V, but I'm going to use a different color. I'm going to get my red. So my V is going to be 0.650. Remember, I've cancelled the moles, so I'm going to remove it, times this number 0.0821. I still have my liters dot atmosphere on top. I've not cancelled it. Divided by 1.908 ATM. Now if I cancel again, let's see. ATM, we cancel ATM. You see, I'm left with liters. The volume will be in liters. And when you punch everything in, what are you going to get? You're going to be getting, your V is going to be giving you 8.33 liters. That becomes our answer. That is the volume of this. So you see, here, like I said, every of the volume has to be in liter. Every of the pressure has to be in atmosphere. If you have a mass, you have to convert it to moles. Like we don't have it in this case, we're going to see that as we move on, and the temperature must be in Kelvin. Let us move to the next problem. Again, you feel free to pause this video, try these problems, and get back to it. It says calculate the volume occupied by 18.2 grams of sulfur dioxide gas, SO2, at the pressure of 2.10 atmosphere and a temperature of 9 degrees Celsius. Again, this is what? The ideal gas. So whenever you see a test student, whenever you see the constant given to you is an ideal gas. So that's an easy way to actually recognize that. So let's take it forward and know what we're given first. We're given the mass of this guy. Remember again, the formula we're going to use here is ideal gas is still PV is equal to nRT. That's what we're going to use. So we're given the mass of sulfur dioxide. We're not given the mole. What we're going to do first is to try to convert this mass to mole. And what do? We calculate the molar mass of SO2. And that will be sulfur. If you look at your periodic table, sulfur is 32.01 to the 2 decimal places. 32.07, not 01. It is 32.07. 32.07 plus 2 atoms of oxygen, and 1 atom is 16, so it's 16.00. And when you add everything together, it's going to give you 64.07 grams per mole. So to get our moles, what do? We're going to convert this mass to mole. And what do you use? You use the molar mass as a conversion factor. So what do? We say 18.02, no 18.2, no 18.02, 18.2 grams of SO2. We're going to convert it to moles. So mole is going to be on top. 1 mole of SO2 divided by 64.07 grams of SO2. And if you cancel out everything, this will cancel this, and we're going to be left with, what? SO2. And that will be, let's do it. It's going to be, what is the number of moles? So if you punch it in your calculator, you're going to get 0.284 mole of SO2. We'll figure that one out. What other things were we given? Let's see. We're given the pressure. The pressure, good enough, is in atmosphere. We don't need to convert it. 2.0, 2.10 atmosphere. 10 ATM. And what else were we given? The temperature is also given. The temperature is T is giving us to be 69. So we're going to say 69 degrees Celsius plus 273, and that will give us 342 Kelvin. Now remember, what are we looking for? We're looking for the volume. We don't have it, so it's going to be in liters again. So we plug everything in and do like we did before. Now I tell students, okay, let me do it the other way. Now, assuming I have the formula to be PV equal to nRT. Now remember, I'm looking for the volume. What do? I can do it from here and just get what the formula will be like. So I can say divide both sides by P, divide this by P. Now what that simply means is that P can cancel P, so that if I solve for my V is going to just be nRT over P. And what do I simply mean? I just plug in the formula. So you can prefer to rearrange the equation first before you solve the problem, or you put your number first before rearranging it. Any one you do is okay. So if we plug everything in, it's going to be 0.284 mole times, I don't think I have enough space here. I'm going to just take it all away and give it myself enough space. Okay, so it's going to be, let's start from here, 0.284 mole times, again, we have a constant here, 0.0821 liters dot atmosphere per mole per Kelvin times 342 Kelvin. And this will be divided by pressure, which is 2.01 atm. So if you cancel out all your stuff, always remember you cancel out your stuff. This, of course, we cancel this. Mole, we cancel mole. And then atm, we cancel atm. And your answer is going to be in liters. So this is 3.80 liters. And this is what you get at the end of the day. Now, we'll go to the next problem. Now, feel free once again to pause this video and try out these problems yourself. All right? And then come back to it. In this case now, still the ideal gas, because we were given the constant. Again, we're given this. And not just that. Again, you see, we're going to do some other conversions here. Now, let's see what we're going to do in this problem. It says, assume that 22.2 grams of carbon dioxide, dry ice, which is solid carbon dioxide, was placed in an empty 525 ml. Remember, carbon dioxide can sublimate. It can go into solid at very high pressure. And then if you release it, what is going to happen is going to escape immediately. So, assuming 22.2 grams of dry ice was placed in an empty 525 ml steel cylinder, what is the pressure if all the solid sublimated at 48 degrees Celsius? Again, what do we do next? We do it. So again, we're going to be using PV equal to nRT, and we're going to make sure that all our things are in the proper unit. So we can start first. Now, but again, we have this as what? Grams. So we have to convert it to moles. Let's start. So what is the molar mass of CO2? Molar mass of CO2 is, carbon is 12.01 plus, oxygen is, there are two of them, and the 16.00. If you multiply it, if you add everything together, it's going to give 44.01 grams per mole. So converting this thing first, what are we going to do? So we're going to say 22.2 grams of CO2. I want to convert it. So I'm going to have 1 mole of CO2 will give me 44.01 grams of CO2. Now I'm going to cancel out and see. This will cancel this. And whatever I have will be 0.504 moles of CO2. That's what I have here at this point. And then again, I have my volume. Look at that. My volume is not in the proper unit. So my volume is in mils. 525 mils. And I want to convert it to liter. What do? I know that to convert it to liter, a liter is equal to 1,000 mils. And again, when you cancel out this will cancel this. If I go back to my red, this will give me 0.525 liters. Now, remember, we're looking for what? The pressure. Pressure is what we're looking for. But we still have our temperature. Our temperature is what? T is 48 degrees Celsius. If you have to convert it to Kelvin, that's as a matter of importance. You're going to get 321 Kelvin. Now that we're ready, we can plug everything in. Remember again, the formula is PV is equal to nRT. We're looking for P, right? So to eliminate V, you can just say divide both sides by V, divide this by V. And if you cancel out your V, what you have at the end of the day is P is equal to nRT over V. And if you plug those in, we're going to do it immediately. Okay, I'm going to move this thing. Okay, I can do it down here. I do have some time down here. It's going to be 0.504 mole. I'm going to multiply it by R is 0.0821 liter to atmosphere over moles per Kelvin times by 321 Kelvin. We divide it by 0.525 liters. Again, we try to cancel out everything. Canceling everything, this Kelvin, we go with this Kelvin. Of course, this mole is going to go with this mole. This liter is going to go with this liter. And what we have will be left in ATM. And that is right, because in this case, we're looking for pressure. Pressure is measured in it. So it's going to be, our pressure is going to be 25.3 ATM if you do your math very correctly, and this becomes our answer. Always feel free to pause some of these questions and then try them to yourself before you come back for comprehension. Now the next problem, again, this problem again is an ideal gas law problem. And it's still an ideal gas law problem. So in ideal gas law, again, remember, we still stick to the formula, the ideal gas. And the ideal gas remains PV equal to nRT, because we're given this constant. That's why the moment you see this constant, know you're dealing with ideal gas. So calculate the mass of N2O2 in 14.1 liter cylinder maintained at a temperature of 35 degrees Celsius and a pressure of 6.3. So now we're looking for the mass of this guy. Now in this formula, there's only one thing that's related to the mass, which is the number of moles. And if you look at it, we don't have the moles. So the issue we're going to do here is that we're going to first calculate the number of moles, and then we're going to take the mole and convert it to mass. However, I want us to calculate first the molar mass of this guy. And in doing that, there are two atoms of nitrogen 14.01 plus 2 of oxygen 2. And when you add everything together, this will give you 16.02 grams per mole. That's exactly what we have there. So to get the mole, let's write out what we're all given. We don't have the moles granted, so we can just say N. We don't have it. And we know it's going to be in mole. But we have other stuff. What else do we have? Let's see. But we have our P is 6.93 ATM. What else do we have? We have our V to be 14.1 liter. Good enough is in liter. We don't have to convert anything again. And what else are we giving? Our temperature again, 35 degrees Celsius. So our temperature will be T will be 35 degrees Celsius plus 273. Of course, that's going to give us, if you add it, it's going to give you 308 Kelvin. Now, we now solve the problem. Again, you can do whichever way you want. PV gives us nRT. We're looking for N. If I want to solve this problem, I can divide both sides by RT. So that's what I'm going to say. If I divide this side by RT, RT, and divide this side by RT, what do I get? Let's see. So RT cancel RT here. So at the end of the day, if I want to look for N, my N is going to give me PV over RT. And then if I plug that formula, if I plug everything in, it's going to be, let me go back to my red. It's going to be, let's do it here. So it's going to be, so technically we're looking for N. So the N is going to be, our pressure, of course, is 6.93. So it's going to be 6.93 ATM times PV. Remember, the volume is in liters, 4.1, good enough, granted. We don't have to start changing it. R will be 0.0821. Of course, the unit is always liters.atm, then per mole per Kelvin, then times temperature. Our temperature is 308 Kelvin. And then if you cancel out what you have, in canceling out, the Kelvin here can easily cancel the Kelvin here. Of course, what else do we cancel? ATM here, we cancel ATM here. Liter here, we cancel liter here. Remember, this is 1 over mole. Because this is 1 over mole, it's going to move off to become mole on top. And at the end of the day, when you do all your problem well, our N, of course, here is going to be, the number of moles is going to be 3.86 moles of N2O2. That's what you get. However, this is not our answer. This is just a means to an end and not an end. What is our end? Our end is that we're looking for what? The mass of NO2. What do we do next? We use the molar mass that we've already calculated here to convert it. So now we want to go from mole of N2O2 to mass of N2O2. That's what we're going to do. So what do we do next? We start 3.86 mole of N2O2. We want to convert it to mass. To convert it to mass, we want to cancel mole. So the mass is going to be on top. So we're going to have our 60.02 grams of N2O2 over 1 mole of N2O2. And let's see what happens here. And then if you cancel out mole of N2O2, cancel mole of N2O2, your answer will be left with grams. So if you multiply this, we're going to get approximately 232 grams of N2O2. And that is how we solve this problem. Now, we're getting to the problem we're trying to finish up. This is second to the last problem. Always feel free to pause the videos at any point in time and try these problems and always come back to it. Now, this problem, now when you hear partial pressure, that should tell you we're now getting to the next concept, which is what? The Dalton's law of partial pressure. This is the Dalton's law. Of partial pressure. That's what we're talking about here. So in Dalton's law of partial pressure, it's a simple addition law. It says, what is the partial pressure of xenon if the total pressure of the gas is given? So remember, I used my PT equal to PA plus PC plus, okay, PT equal to PA plus PB plus PC to show you example. It doesn't have to matter. Look at what I'm going to do here. You say the total pressure is supposed to be the partial pressure of xenon plus the partial pressure of N2. But you've been given the partial pressure of what? Nitrogen. You're looking for that of xenon. Let's put it together. And the total pressure is given to be this. So what that simply means is that if you say 7.6 atm, well, let me put my units. atm will be equal to, we're looking for partial pressure of xenon, but we can do the partial pressure of nitrogen. Nitrogen is going to be P. No, just put the number, it's already given. We have it there. It's going to be what? 2.3 atm. So if you subtract 2 from both sides, what are you going to have? You're going to have the pressure of xenon at the end of the day will be 7.6 atm minus 2.3 atm. And that will give you 5.3 atmosphere. And that becomes the answer. So the Dalton's law of partial pressure problems is very trivial. It's simple addition and subtraction that we actually use in doing these problems. And at times I can make it a little bit longer by giving you some problems whereby you have to think a little bit and then do some other conversions away from the last. I can say, okay, convert this to torr or convert it to PSI. Let's see that in the next problem, which happens to be our last problem in this lecture. It says a steel cylinder contains a mixture of neon, oxygen, and helium gases. It says the total pressure is given to be this. So we know that the total pressure is given to be 4740 millimeter mercury. And then, so the pressure of oxygen and helium, that of helium, let's write it out. So that of P oxygen is 1200 millimeter mercury, and P helium is given to be 1850 millimeter mercury. Now it says, what is the partial pressure in millimeter mercury atmosphere of neon? So we're looking for P neon. That's what we're looking for. We're looking for the partial pressure of neon in mmHg and atm. So what it means, we're going to calculate others are in mmHg. We're going to calculate it in mmHg and then we convert it to what? ATM. That ATM doesn't look good. I'm going to make it good. So this is going to be ATM. All right. So let's start that here. So what it simply means, if we make a formula of this now, we're going to have P neon plus PO2 plus P helium. That's what we have here. So if you add all those things together, so it's going to be 4740 millimeter mercury will be equal to P neon plus 1200 plus 1850. Remember, these are in ATM. It's going to be a little bit longer. Okay, let me just write it. It doesn't matter. That's the last problem, so I can't be in a hurry anymore. Let me just say 1200 millimeter mercury plus 1850, that's what we have here, millimeter mercury. So if you add these two together, it's going to give you 4740. I'm not going to put the unit again, I've showed you that. Will give you P neon plus, if you add these two together, it's going to give you 3050. Therefore, P neon will be, you subtract this from this when it moves over. So this is going to give you 4740 minus 3050. And then if you do the subtraction correctly, it's going to give you 1690 millimeter mercury. That becomes the answer in millimeter mercury. However, we're going to convert this to ATM because that's the proof. So we've done the first problem, which is this. The second problem, we're going to convert this. So it's going to be 1690 millimeter mercury. Now, of course, remember 1 ATM is equivalent to 760 millimeter mercury. So what we're going to do is, since we want this in ATM, our ATM is going to be on top, 1 ATM. One ATM will be equivalent to 760 millimeter mercury. And when you cancel your work rightly, you're going to be having everything left. So this is going to give us about 2.22 ATM. And this is the second part of the question. So the first part gave us this, the second part gave us this. And that is how we do this. So the problems, actually, the problems in Dalton's law of partial pressure are trivial and simply involves addition and subtraction. However, when you are asked to convert from one unit to another, you have to watch out for this and make sure you complete the problem. Once again, thank you for listening to this class and do have a wonderful day ahead of you. Bye.